Hello, everybody. This is Mr. Fluharty. I am going to make a series of videos to go over the material that we'll be covering in the remainder of the course. So we'll see how this works. This is the first time I've ever done it, so there's going to be some hiccups. I might have to stop and rewind, but I want to just keep going. I'll try to make these videos maybe 10 minutes at the most, but what I plan on doing is giving a little bit of background information and then describing what you need to know in the unit packet. So let's get going. The next unit that we will cover is called covalent compounds. So we're going to discuss materials that are made covalently. The thing that distinguishes the type of material, as we discussed, is what are the elements that make it up. And the two types of elements that we've talked about is metallic elements and non-metallic elements. So that gives you three types of compounds. There's metallic compounds, where it's a metal with a metal, and that can either be a pure compound like gold or silver, or it can be an alloy of two different metals like bronze. And metallic materials, they tend to be very hard, and you can bend them, you can flatten them out really thin. The terms that we use is ductile and malleable. The next one we talked about was ionic compounds, and they, as we talked about in chapter 5, it's a metal with a non-metal. The metals are on the left side of the stair step, and the non-metals are on the right side of the stair step. When we get a metal with a non-metal, we call that a salt. In an ionic compound, the electrons, the outer electrons, are completely separated or accepted from the material, from the elements. A metal gives away electrons to achieve an optimal outer orbital, like a noble gas. A non-metal accepts electrons to achieve an optimal stable configuration of 8 electrons, like a noble gas. And then finally, we're going to talk about covalent bonding. Covalent bonding, the last choice available, is a non-metal with a non-metal. In covalent compounds, instead of giving away and accepting electrons, they actually share electrons. And one thing to remember is that they always share electrons in pairs. It's always 2 electrons. It could be 2 electrons that they're sharing, 4 electrons that they're sharing, or 6 electrons that they're sharing. But again, they share them in a way that optimizes the stability of the configuration, which means they have 8 electrons in their outer valence shell. So what do we want to learn? Well, let's go to the next screen. So here are our objectives. For covalent bonds, explain the role and location of electrons in a covalent bond, describe the change in energy and stability that takes place as a covalent bond forms, distinguish between nonpolar and polar covalent bonds based on electronegativity differences, compare the physical properties of substances that have different bond types, and relate the types to electronegativity differences. So there's a lot of words in there that we're not familiar with. Covalent bond, molecular orbital, bond length, bond energy, non-polar covalent bond, polar covalent bond, and dipole. So what I'd like to do is let's just flip through the chapter really quick and look at some pictures. Okay, so here is a picture. Let me get it there. Here's a picture of what happens when 2 non-metals come together to make what we call a molecular orbital. So as they come together, the nucleus of one, which has a positive charge, is attracting the electron of the other atom. At the same time, the nucleus, the positive nucleus of one atom, is repelling the positive nucleus of the other atom. So there's a push-pull relationship, and as they come together, they reach an optimal distance where the repulsive forces between the two nucleuses is just balanced by the attractive forces between the proton and the other electron. And this is called a covalent bond. And the basic difference between an ionic bond is that the two electrons are shared equally between the two atoms. And if we go down here, we can see an energy diagram of what's going on. So think of this as a hill or a roller coaster. At the top of the roller coaster hill, you have the two atoms and they're separated. They don't know each other there. But as they come closer, as they go down the hill, they start having this electron-proton attraction. And then as they go further down into the energy well, they come to this optimal distance. And for the hydrogen molecule, we call it, they are optimally 75 picometers apart. If we try to push them even closer, though, then the nucleus-nucleus repulsion takes over and the potential energy actually goes up. And we can't push them closer together. So it goes up and it might roll back down, and then it rolls back and forth and cut until it comes to this optimal distance. What is the implication of this type of bond? Well, you can see here there's a slinky, and that's would model a covalent bond. It's very flexible. It can be stretched. The top, where they're holding a ruler, would represent an ionic bond. It's very inflexible. The only way to stretch it is to break the bond. And you can see this if you touch your skin and feel how pliable it is. That's a covalent bonded material. Okay, I'd like you to look at this graph. If I can get it up here, you can see that if you look at the numbers, what we have here is for different types of bonds, for different types of covalent bonds, right? This is a nonmetal attached to a nonmetal. As the bond energy goes up, like here's a very high bond energy, the bond length goes down. So what this says is that if you have a very short bond in a covalent bond, it has a lot of bond energy. The bond energy is the energy needed to break the bond, or the energy needed to form the bond. So note that the bonds that have the highest bond energies, the strongest bonds, usually involve the elements hydrogen and fluorine. Also note that the stronger bonds generally have shorter bond lengths. Okay, we can talk about a non-polar covalent bond or a polar covalent bond. And to do that, we have to talk about electronegativity. Electronegativity is a measure of an atom to attract electrons. So you can see that fluorine has the highest electronegativity of a 4. That means it has the highest ability to attract outer electrons. Francium, on the lower left side, has the lowest electronegativity at 0.7. So the general trend is for the electronegativity, the ability of elements to attract electrons, to increase to the right and up. And here is a graph that helps you understand the differences based on electronegativity differences between the different types of bonds. And when I say electronegativity differences, you take the electronegativity of the particular elements in the bond and you subtract. So if you take the two differences and it's less than a half, it's a non-polar covalent bond. If it's between 0.5 and 2, it's a polar covalent bond. If it's greater than 2.2, roughly, it's an ionic bond. So when you're bonding a non-polar metal with a non-metal, they tend to be, their electronegativity differences tend to be below 2. If you're bonding a metal with a non-metal, their electronegativity differences are greater than 3. And again, just let me reiterate that we take these numbers and we subtract them. So if you take fluorine and bond it to lithium, that's lithium fluoride. 4 minus 1 is 3. 4 minus 1 is 3, and it's greater than 2, so you can see it's an ionic bond. If you take carbon and bond it to nitrogen, cyanide, we call that CN. If you take carbon and bond it to nitrogen, that's 3 minus 2.6. 3 minus 2.6, that's 0.4. That would be a nonpolar covalent bond because it's less than 5. That's how that works. Now, what does that mean? Well, nonpolar covalent bonds means that there's no electricity difference or charge difference within the molecule. A polar covalent bond does have a charge distribution that tends to have one side of the molecule have a positive charge and the other side of the molecule have a negative charge. What that creates is like a little mini magnet. One side has a positive, one side has a negative, and they're going to search for situations that cancel out these charges. And then if it's separate electron clouds, they just cancel each other because a plus and a minus. 1 minus 1 is 0, so it's an ionic material. What we call these situations where there is a charge imbalance, we call that a dipole. Okay, and I think that's about it. I guess we'll end with some short discussion of, okay, well, what does that do to the materials that are made out of these different types of bonds? Well, if it's a metallic bond like potassium, notice the relatively low melting point, relatively high, a middle kind of boiling point. The properties are soft. Metals can be soft, silvery, solid. They conduct electricity. Ionic materials like potassium chloride, very high melting points, very, very high boiling points. They tend to be crystalline. Most of them are white. When they're solid, they're white crystals. They conduct electricity when dissolved in water or melted. Covalent materials like chlorine is an example. It has a very, very low melting point, a low boiling point. For chlorine, it's a gas at room temperature. It's a greenish yellow gas, and it's not a good conductor of electricity. So that's all for now. My next video, I'm going to go into the unit packet. So I will post the unit packet, and if you could download it and print it out, and I will be going through, and as I go through, you can take notes, and we'll just march through the unit packet. Talk to you later.